Hi everyone, welcome to EMQ webinar. I'm so happy to have you all. Today we are going to talk about MQTT broker cluster scalability. As we all know, IoT infrastructure's scalability is essential for handling plenty of connections to meet the growing business demands. In this case, EMQX may be the best choice. Of course, it has been recently tested with 100 million connections. In this webinar, we will explain why EMQX is so scalable through several aspects, such as EMQX's foundation, clustering, and demonstrate how to reach 100,000 in the live show. Today, our speaker is Kerry Ware, who is EMQ pre-sales engineer. He has strong hardware and software engineering background and worked with customers in a wide range of industries. Before we kick off the webinar, I would like you all to know that we will be recording this session and all participants will be on mute by default. If you have any questions during this webinar, please type them in the Q&A box or raise your hand. After permission, you could talk with speaker directly, and the questions in the Q&A box will be answered in the Q&A part at the end of the webinar. We will share the recording of the webinar and slides in the follow-up email. So let's welcome Kerry.
Thank you, and hello, everyone. Today, we're going to be talking about MQTT broker cluster scalability and how it's done in EMQX. So first, I'll talk about the foundation of EMQX. Then I'll talk about EMQX clustering, how it's currently done in version 4. And then I'll talk about our improved clustering and how we're going to be doing it in version 5, which will be released sometime later this year. And I'll also do a demo of load testing using our EMQTT bench tool. I'll demonstrate 100,000 connections and 100,000 messages per second. So because it takes a little bit of time for the clients to connect, I'm actually going to start this during the presentation. And finally, at the end, we'll have summary and questions and answers. So now, like I said, I want to start the subscribers right away, just because it takes a little time. So I'm going to be using our EMQTT bench tool to generate the clients. So I just want to talk a little bit about that tool before I start subscribing the clients. So EMQTT bench is our benchmarking tool that's written in Erlang. You can use it for load testing that can generate millions of clients, either to publish, subscribe, or just connect. So the publishing clients will connect to the broker and then start publishing messages right away. The subscribing clients will also connect and also subscribe to the broker. And the connect clients will just connect. So you can either connect to an MQTT broker or a load balancer. And our EMQTT bench product is completely open source and free. And here's the link if you want to try it. So the commands I'll use for subscribing, it's basically just a simple command line interface. So you use subscribe, then the connect to generate 50,000 clients. Then you specify the host address and the topic that you want to subscribe to. And it also has a counter that's associated with each client that subscribes. So the first client is client 0, then client 1, 2, 3, 4, etc. So what that allows you to do is it allows you to generate, so each client can subscribe to its own topic. So the first one will be test 1, then test 2, test 3, etc. So what we'll end up having is we'll have 50,000 clients with 50,000 topics. Then quality of service is 1. So it will mean that there's guaranteed delivery, but it's guaranteed at least once. So there could be duplicate messages. And then the IP address, every client that connects is associated with an IP address and a port, but there's a limitation of about 60,000 ports per IP address. So if you want to use more clients than 60,000, and that's combined both publish and subscribe, then you need to provide the tool with more IP addresses to use. So that's what this does, is it allows the tool to use more than one IP address. So that's the subscribe command. So we'll have 50,000 clients subscribing to 50,000 topics. Then the publish command is basically very similar. You just use publish, again, specify the number of clients, which in this case will be 50,000, the broker host address, the topic, which will be the same as the subscribe topics, quality of service, and then the interval of message. So each client will publish one message per second or 1,000 milliseconds. So the total published messages will be 50,000. So that will be 100,000 combined, both publish and subscribe messages. So now I'll generate the subscribers. So if I go to the EMQTT bench tool, let me move the Zoom tools out of the way. So here is in EMQTT bench, I've got the subscribing clients and the publishing clients. So I'll start the subscribing clients. So now EMQTT bench is generating the subscribers. So if we go over to EMQX, we can take a look at those, and we should see those. We should see the number of connections increase. So it's increasing the number of clients. We can look at, so here's the clients, here's the topics, so tests with different numbers, and then we can see the subscriptions. So if you notice that each client has a number, this is that %I that I was talking about, that's in this case 37338. So that's going to subscribe to test 37338. This one's going to subscribe to test 30722, etc. So while the clients are coming online and subscribing, I will continue on with the presentation. So next, I'll talk about the foundation of EMQX and how it's built. So EMQX is built using the software language Erlang with OTP libraries that runs on the Beam virtual machine, and I'll describe those a little bit later. So Erlang was created by Ericsson in 1986 to help them develop their telecom products more efficiently. There weren't many software languages available back then, so they ended up creating their own. And Ericsson's software requirements were it needed to work in a large real-time system so that they could develop their systems more efficiently. It had to be able to handle concurrency, or in other words, it had to handle hundreds of thousands of calls simultaneously. It had to be distributed over several computers. It had to be fault tolerant, so the failure of a single switch would not bring down the entire system. It had to support high reliability and high availability, so for continuous operation over many years. It also had to support a hot upgrade, so they could upgrade the software without stopping the system. So in summary, they were wanting a concurrent, fault-tolerant, scalable system. So the creators of Erlang in 1992 made a demo. They called it Erlang the Movie, and if you Google it on YouTube, you'll find it. So in the demo, what they did is they set up a point-to-point phone call, and then they left that call connected, and then they attempted a three-way conference call. But the conference call didn't work, and that was because there was a bug in the code. So with the point-to-point call still connected, they didn't disconnect it, still connected, they corrected the bug in the system, and then they restarted the system. So with the point-to-point call still connected, they attempted the three-way phone conference call. And this time the call worked because they fixed the bug, obviously. And the point is, the point-to-point call was never disconnected. So in conclusion, they had one point-to-point call, but it could have been a million point-to-point calls, and none of them would have been disconnected. And that is because of the Erlang feature of process isolation. So another thing to note is that this bug was a reproducible error in a common feature. So in reality, it probably would have been caught during testing. But Erlang's strength is that it can detect and recover from transient, hard to reproduce errors. So the characteristics of Erlang are its many lightweight concurrent processes, which can be in the millions. They're all isolated processes, so there's no shared memory or pointers. It supports asynchronous communication among the processes. It's fault tolerant, so a part of the system may crash, but not the entire system. It's non-blocking, so one process cannot lock up the entire system. Erlang coined the term soft real-time. So what it meant was a missed hardware deadline is not really considered a failure. It may degrade the system, but it's not actually a failure. And it also supports hot code upgrades. So you can update the code without stopping the system. So some of the components of Erlang is the Beam virtual machine, and Beam stands for Bjorn Bogdan's Erlang abstract machine. Bjorn and Bogdan were the original creators of the Beam virtual machine. Erlang also has schedulers, basically one scheduler per CPU core. And each scheduler is in charge of running many concurrent processes. And then it also has a Manisha database, which is local inside the virtual machine. So the lightweight concurrent processes, there can be millions, and they're all very lightweight. The minimum size is just a few hundred words. They're isolated from each other. All the processes have their own local memory space. No memory is shared. And in EMQX, we have approximately one process per client. So if you have 100 million clients, then you'll have 100 million processes. Erlang has asynchronous message passing between the processes. So that means it's non-blocking. So once the process sends the message, it will still continue to run. The message data is copied, so there's no shared memory between the processes, and each process has its own local memory area. There is a common storage, the Erlang Team Storage or ETS, but the processes don't work directly in the storage. They actually copy the data into their local memory. And the reason for that is for isolation. So isolation is important because it means a single crash process does not affect the other processes. So the rest of the system is still running even though one process may crash. But the crash can be or is recorded in an error log for further analysis. Erlang is fault tolerant. So the system is still running even though one process may have crashed. And there could be several reasons for the crash. It could be because of a transient error. In that case, a restart may actually cause the process to continue working and fix the bug, if you will. It could have crashed because of a reproducible error. And in that case, the error log and testing will help to debug the issue so it can be fixed in future releases. So it's a very fault tolerant system. Processes are organized in a tree called a supervisor tree. So there's two types of processes: worker processes that do the work, and supervisor processes that monitor a set of workers. And the supervisors are notified when one of the workers crashes, and then it can choose to either restart only the crashed worker or restart all of the workers. So in this case, in this example, this supervisor has 3 workers, but if one of them crashed, it only reset the one crashed worker. But in this case, the one worker crashed, but it reset all of the workers, maybe because they were doing tasks that were related, so they all would needed to have been restarted. Erlang all the processes run in a scheduler, both the supervisor and the worker processes. Each scheduler has its own FIFO run queue, first in, first out. Processes can have a priority. There's 4 different levels from max to low, and typically 1 scheduler per CPU core. So in this example, the processes are put onto the queue, and then they're considered in the runnable state. And then the oldest process with the highest priority is then taken off the runnable state and put into the running state. So the schedulers run in parallel, assuming you have 1 per core. Erlang also has load balancing. So if a scheduler has no process to run, then it will try to steal a process from another scheduler. So the idea is not to have idle schedulers around. So the system will try to minimize the number of schedulers and put the empty ones to sleep, just to minimize the number of empty schedulers. So in this case, in this example, scheduler 2 doesn't have any processes, so it tries to steal 1 from scheduler 3 in order to sort of load balance the processes. Erlang has an anti-blocking mechanism with preemptive scheduling. So it prevents processes from using 100% of the runtime of the scheduler. So a process is moved to the end of the queue after performing a certain amount of work. In Erlang, this is called reductions. So a reduction counter is initialized to 2000. And it's decremented anytime there's work done, such as function calls or garbage collection, etc. And then when the counter reaches 0, then regardless of what the process was doing, it's put into the back of the queue. So this keeps the process from, even if it's in an infinite loop, from blocking the entire system. And this is sort of the mechanism of why it's considered soft real time, because the process could have been counting down a timer and then ended up being moved to the back of the queue. So the timer would actually be, instead of 10 milliseconds, maybe it'd be 10.5 milliseconds. So that's the reason for the soft real time. Erlang has a concept of hibernation. So a process is moved to the waiting state if it's waiting for messages that are not in its message queue. And each process has its own message queue. So then the process is moved back to the runnable state when the message arrives. So in this example, there's a process that's running. It's waiting for some message, but that corresponding message is not in its queue. So it gets put to the waiting state and it stays there until that message arrives into its message queue. Then that process gets put back onto the scheduler. And the idea behind this is to reduce the memory and the CPU load as much as possible. So there could be millions of processes, but not all of them are necessarily active at the same time. So EMQX supports hot upgrades at the patch version. So the patch version is the 3rd digit of the version number. So for instance, if we have version 4.4.x, X is the patch version. So you can upgrade, you can perform a hot upgrade from 4.4.0, for example, to 4.4.1 or 4.4.2. But you cannot perform a hot upgrade from 4.2 to 4.3 or 5.0. So in this example, we're running version 4.4.0, and we want to do a hot upgrade to 4.4.1. So we perform the upgrade, and then once we check the versions, we'll see that 4.4.1 is now the running version and is tagged as permanent. And so permanent means that if EMQX is restarted, then that version will be the one that's reloaded. So you can choose to have an older version tagged as permanent, but maybe for doing some testing or something like that. And the benefit of the hot upgrade, of course, is you don't have to disconnect any of the clients in order to do a patch on the system. So just a little bit of a little more details on the hot upgrade. in this example, we're upgrading from 4.2.0 to 4.2.1. So the steps, if we do an EMQX version, we can see that we're currently running 4.2.0. Then we would download the next, the newest patch version to 4.2.1. Then copy it to the releases directory, perform the upgrade, and then basically that's it. So it's then we can check it and verify that, yeah, we have actually indeed upgraded the software. So it's fairly easy to perform hot upgrades. It's just a couple of steps. So now what I'll do is I'll go check the demo and see how the subscribers are doing, and then I'll start the publishers. So if we go back to EMQTT bench, let's see how they're doing. So it looks like all 50,000 clients have now subscribed. So if we go look at that in EMQX, we can see that we have, let me slightly move this. I just want to point, there's 2 nodes in our cluster. So half of the subscribers are connected to node 1, approximately half, and half are connected to node 0. So the total number of connections is 50,000, split between the 2 nodes. So that's the number of clients that are connected. And if we go look at the number of Erlang processes, we can see that it's also about 25,000, just above the number of connections. So there's approximately what I'm trying to say is there's approximately the same number of Erlang processes as the number of clients, so just slightly greater. So we can go look at the clients. That's here. We can see the different topics. So test 5783, test 31969. And now we can look at the subscriptions. So this is the %I that's in the command. It's a counter associated with that client. So it's the counter is 5129, and it's subscribing to topic test 5129. This counter is 26082, and it's subscribing to test 26082. So now it looks like our clients are okay, our subscribing clients. So now what we'll do is we'll start the publishers. So here's the publish command to generate 50,000 publishing clients. So that looks like that's working okay. So while they're connecting and coming online, I will continue with the presentation. So next I'll talk about EMQX clustering and how we currently do it today in version 4. So one thing, just to define an Erlang node. So an Erlang node is defined as a runnable system consisting of the things that I talked about before, namely the Beam virtual machine, the schedulers, and the concurrent processes, plus the local Manisha database. So all that's considered an Erlang node. And an EMQX node so one EMQX node is built upon one Erlang node. So the EMQX node can support approximately 1 million connected clients and 1 million messages per second. So that's not a hard limit. That's just based on performance. And that's the clustering today. So here's an example of a distributed EMQX. So the nodes are, the ID of the nodes is name at host. So the name could be basically a name, but the host has to be a fully qualified domain name. So for instance, IP address or a domain. So that's the way the nodes are identified. They're connected to each other by TCP connections. You can also use TLS, but it's more overhead. It uses up more computer resources. The nodes communicate to each other by message passing. And you'll note that they're connected in a mesh topology. So every node is connected to every other node, directly connected to every other node. And if a node wants to join the cluster, it only has to connect to one node, and then it will automatically be a part of the cluster. So message topic routing. So clients connect to one node in the cluster. So for instance, we have a sensor that's connected to node 3. So incoming messages needed to be routed to the appropriate nodes and delivered to the subscribing client. So in this case, we have a sensor publishing to sensor 1 temperature topic connected to node 3. And on node 2, we have 2 clients that want to subscribe to that topic. So, the cluster needs to know to deliver messages on this topic to node 2 so that they can be delivered to the corresponding subscribing clients. And all this is done using routing and subscription tables. So each node has its own subscription table, which maps the topic to the subscribing clients. So here we have client 1 and client 2 that are subscribing to sensor 1 temperature. So its corresponding entry in the subscription table would be sensor 1 temperature and client 1 and client 2. So the subscription table is how the node knows which clients to deliver the topic messages to. And then after the clients subscribe, the node then needs to update the routing table so that other nodes know which node to deliver the message to. So it updates the cluster routing table with just the node information. And then that routing table gets replicated to all the other nodes. So all the other nodes need to know that node 2 has clients that are subscribing to this topic. And it's also important to note that each node has its own copy of the routing table. And that's the table is replicated automatically by the Manisha database. So this shows how the tables work together so the broker knows how to route the messages. So here we have sensor publishing data to sensor 1 temperature on node 3. So node 3 looks at its routing table and says, oh, okay, I need to send that data to node 2. And the node 2 then looks at its subscription table and says, okay, now I need to route the data to clients 1 and client 2. So that's how the subscription table and the routing table work together. So a bit about the Manisha database. It's an embedded, distributed, transactional NoSQL database. It's embedded, which means that data access is about as fast as with local variables. It's distributed, so it replicates the table data across all the EMQX nodes automatically. All nodes have their own copy of the data, own local copy of the table data. And it's fault tolerant against nodes going down. It's transactional, which means that read and update operations can be grouped together into one transaction. And they're atomic transactions. So either the entire transaction completes or the entire transaction fails. There's no combination or inconsistent states. It's NoSQL database, so it means it operates with Erlang directly. There's no SQL query language involved. And if you check this link, you can see a blog where we've described a little more how it works. We recommend using a load balancer for a cluster. So basically the load balancer distributes the clients among the loads automatically. The client only needs to know the address of the load balancer. It doesn't need to know the address of the individual nodes. You can also terminate a TLS connection at the load balancer. So you can have TLS on the front end and TCP on the back end. Some examples of load balancers are Nginx and HA proxy. So there is a scaling limit to the maximum number of nodes you can have. And this refers to version 4, or in other words, pre-version 5. This is what the limitation is today. So generally, the maximum number of nodes you can have per cluster is 10. The maximum number of connections per node is 1 million. So that means that you can have at most per cluster 10 million clients. It's not a hard limit, but it's based upon performance. And so the reason the limitation is there is because for in nodes, the number of connections between nodes is defined as n times n minus 1 divided by 2. So that means as n gets larger, the scaling factor and therefore the table replication factor increases by a factor of n squared. So if n is much greater than 1, then basically the 1 goes away. So the n2 factor actually limits scalability, but we solved this in version 5. So a bit on the hardware limits, hardware requirements. So you can estimate the server size depending, that is a function of a couple of things: the maximum number of clients that you want to connect, and the maximum number of messages per second. And we call that transactions per second because it's the total number of messages both published and received per second. So just a couple of examples. If you have 1,000 clients connected and 100 transactions per second, then you need a 4 gigabyte 2-core machine. If you crank it up a bit to 1 million connections and 100,000 transactions per second, then you need a 32 gigabyte 16-core machine. So this will give you a rough idea of how to size your servers. So that was how the clustering is done in version 4. But now I'll talk about how we've improved it in version 5. So back in January, we published a blog that says we were able to reach over 100 million subscribers using 22 nodes. So that obviously is more than the limitation I described earlier. So how did we do it? So the answer is we solved the n-squared connection scalability issue as new nodes are added. So there's a couple of ways that the mesh configuration is used. One is it's for topic message routing. So just to tell the nodes how to route the messages that come in on a topic. And it turns out that this is really not so much affected by as the connections and the nodes are increased. It's really minimally affected. However, what is affected is the table replication. So as the routing table needs to be replicated across the nodes, every time a client subscribes or unsubscribes to a topic, it turns out that that's greatly affected by the number of connections and the number of nodes you have. So that really is the limitation on the scaling. So what we did, the solution we did in version 5 is for topic message routing, we kept the full mesh topology because it doesn't really affect performance as the nodes are scaled. However, for table replication, we actually broke the full mesh topology. So for the purposes of table replication amongst the cluster, it no longer has a full mesh topology. So what that was able to achieve is we were able to reduce the scaling by a factor of n instead of n squared. So the way we did that was to create 2 node types. One, the core node, we define the core node as the existing node type. So it still retains the full mesh topology, where table data is updated synchronously across all the core nodes. It suffers the same n2 scaling problem, but the idea is now n will be much smaller, generally 3 or 4 core nodes. Then we defined a new replicate node that connects to the core nodes, but it does not connect to each other. So there's no full mesh with the core nodes. It only connects to one, with the replicant nodes, it only connects to one core node. It only connects to the core nodes, not to each other. It acts like a client to the core node, and it requires, it acts like a client to the core node, and it requests updates to the data, which are performed only on the core nodes. And data is updated asynchronously, and all the nodes have local copies of the table data, so it provides fast access time. Also, the number of replicant nodes does not affect the write throughput because it's only the core nodes that are actually doing the writing of the table data. And it also supports auto scaling because adding and removing replicant nodes does not change the data redundancy. So this is just another diagram that shows how the sensors are, how the clients are connected. So generally there is only 3 or 4 core nodes, and the rest of the nodes are the replicant nodes. So the idea is there's only a small number of core nodes, and the clients connect to the replicant nodes. It's not a hard rule. It's just sort of a default way topology that we set up. So the clients connect to the replicant nodes, and therefore adding and deleting, scaling is done by adding and deleting the replicant nodes. So every time a replicant node is added, it's only one connection instead of n squared. So now we were able to get scale by n instead of n squared. And also, there's a new extension to the Manisha database called Maria, where that implements this. So you can see it on, it's open source and you can access it here. And I just want to point out that, so the sensors connect to the replicant nodes, and then there's a direct connection to the corresponding subscribing nodes. So it's not shown in this diagram, but there is a mesh connection between the replicant nodes for the purpose of routing the message data. And again, we recommend the load balancer. So generally speaking, the load balancer will connect to the replicant nodes, and the core nodes will be just for writing the table data. It's not a hard rule, it's just sort of a recommended topology. So now I'll go back to the demo and I'll explain the setup a little bit. So the idea is we have 100,000 connections with 100,000 messages per second. And just recap the setup I have. I'm using EMQTT bench, using 50,000 publishers and 50,000 subscribers. They're actually going to a load balancer, and there's 2 nodes. So the load balancer splits the clients between the 2 nodes. So 50,000 publishers publishing 1 message a second. So that's 50,000 messages per second published and 50,000 messages received, subscribed. So that's a total of 100,000 messages per second. So you can try this yourself if you want. So to try this yourself, you would go to download EMQX. It's the community edition. Then you can download the EMQTT benchmarking tool. This is the link to the hardware server requirements. So check that out to make sure your hardware is enough. And the other document that's worth checking out is our tuning requirements, because it can be, if you're using a lot of clients, if you're pushing it to the limits, then you may have to tweak some of the operating system parameters. So now I'll go back to the demo and see how things are doing. So let's go check out EMQX. And I can see that we have split between the 2 nodes. We have the 100,000 connections, basically 50,000 connections on each node. And if we look at the Erlang processes, it's also about 50,000. So that just shows that the Erlang processes are about equal to the number of client connections. And just to point out, I'm using the EMQX broker. It's just the community edition. So it's the open source free version, version 4.4.1. So if we go over to Grafana and look at some of the data here on the dashboard, again, this is per node. So you can see it's 2 nodes. So the numbers you see, you really have to double because it's this is only showing the data for 1 node. So it's showing our 50 clients per node. So 50,000 clients per node. So 100,000 total. Then the number of subscriptions, the number of subscribers. And then finally, the message rate. So we can see that each node is sending about 25,000 messages per second and receiving about 25,000 messages per second. So that's 50,000 per node. And if you double it, it's 100,000 messages per second for the entire cluster. So basically, that was it on how to use EMQTT bench for generating subscribing clients and publishing clients. So you can use that to test your system. So you're welcome to join our community, both on Discord, Slack, and our forum. And we're happy to discuss your favorite topics with you.
So first of all, thank you for your attending again. If you have any other questions, feel free to contact us in our Slack channel, Discord server, or GitHub. And we will share the recording of the webinar and slides in the follow-up email. So thanks for your interest. See you next time. Bye-bye.